So solving linear systems by graphing. So a fact from the last unit. So every point on the graph of an equation is a solution to that equation. So a graph is just a way of picturing all the solutions to a given equation. So from the last unit, we know that the graph of an equation in two variables is the set of all xy in the xy plane that make that given equation true. So one way to solve a system of two linear equations in two variables is to make the graph for each equation in the same xy plane. So then which points in that graph will be solutions to both of the linear equations? Well, if we think about the picture here for just a minute, so let's let line 1 correspond to equation 1, and line 2 is going to represent or correspond to equation 2. So every point on line 1 is a solution to equation 1. So every point on this line, all of those points are solutions to equation 1. If we have some point out here, okay, this is not a solution to equation 1. Okay. Now, every point on line 2, so again, we have infinitely many points here as well, and all of these points on line 2, so every point on line 2 is a solution to equation 2. Okay. So we can have some point here again, this is not a solution to equation 2. Okay. But now, if we want to solve a system that contains equation 1 and equation 2, then we need an ordered pair that makes both equations true. So that means I need a point that's on this line, on line 1, and I need a point that is also on line 2. Okay, well, in our picture, there's only one point that meets that criteria, and that's this intersection point here. So the intersection point is a solution to both equation 1 and equation 2. So the intersection point is the solution to the system that contains both of those equations. So once we make our graph in the same xy plane, which points on the graph will be solutions to both of the linear equation, we're looking for the intersection point. So let's look at solving a system using the graphing method. So again, here's one of our important verbs in mathematics that we need to know what we're being asked to do. So to solve a system, we need to find, in this case, since we have two variables, x and y, we need to find all ordered pairs, all xy, that make all of these, so I'm just going to use the word both since there's only two, so we need to find all the ordered pairs that make both equations true. Okay. So the graph corresponding to an equation gives us all the points that are solutions to that equation. So to find the points that are solutions to both, we need to look for the intersection point. On the graph. So the first question here asks us to explain how you can tell that the given equations are linear equations. Because again, we spent a lot of time in the last unit on linear equations. So if we're looking at each of these equations, our first term is an x term, next term is a y term, and on the other side of the equation we have a constant term. Okay? Every term in this equation is either an x term, a y term, or a constant term. There's no x squared terms or y squared terms or xy terms. Okay? So this is a linear equation. Okay, same thing with our second equation. We have x terms, y terms, and constant terms. Okay, so every term in each equation is an x term, a y term, or a constant term. So if we want to graph both of these equations, one way we can do that is just we need 2 points. Okay, so to graph a line, we need 2 points. More points is nice to do some checking on work, but we only need 2 to define a line. So 2 points that are sometimes easy to find if they're 2 distinct points are the intercepts to that graph. So let's look at the first equation, 2x plus y equals 2. And think about finding the point where it crosses the x-axis and the point where it crosses the y-axis, and that'll give us 2 points to connect to make the graph of our line. So the y-intercept is a y value when all the other variables are 0. In this case, our only other variable is x. So if we substitute 0 for x, we're going to get 2 times 0, so we get 0, plus y equals 2. And so the only y value that will make that equation true is 2. So the ordered pair 0, 2 makes this equation true. Therefore, it has to be a point on our graph. Okay, so here's one of our points right here. And to get the x-intercept, we need the value of x when all the other variables are 0. In this case, our only other variable is y. So we're going to plug in y equals 0, and we will get 2x equals 2. So 2 times some number has to be 2. Well, that number would be 1. So the ordered pair 1, 0 makes this equation true. Therefore, it has to be a point on the graph of that equation. So on the x-axis, we're going to have a point at 1. Okay. So now in our table here, if we were to compute our slope as the ratio of change in output to change in input, we go from 2 to 0. So we go down 2 in output. And input goes from 0 to 1, it goes up 1. Okay, so our slope down 2 and to the right 1, which we can see in our graph, down 2 and to the right 1. So again, if we keep doing that, down 2 and to the right 1, and getting some more points to connect. And in the other direction, we can go up 2 and to the left 1. And that gives us a bunch of points that we can then connect to make the graph of our line. Alright, so there is graph of equation 1. Now if we take a look at our second equation, we had negative 2x plus y equals 6, second equation. So again, if we're going to try to find both of the intercepts, so we're going to plug in x equals 0, we'll get y equals 6. And if we plug in y equals 0, we get negative 2x equals 6, so x would have to be negative 3. So we've got a point on our y-axis at 6, and on our x-axis at negative 3. And so again, our slope here, the ratio of change in output to change in input, so output goes from 6 down to 0, so it drops 6. And input goes from 0 to negative 3, so it also dropped by 3. So we would get the ratio 2 to 1. So we can go up 2 over 1, up 2 over 1, up 2 over 1, get a bunch more dots. Or again, we could have written this as negative 2 over negative 1, so down 2 and to the left 1. And we can do that over and over to get some more points. And so again, if we play dot to dot here, if we connect the dots on our graph, well, let's try to connect them a bit better than that. So there is our second equations graph. And as we're looking at our graph, it does look like they intersect right here at negative 1, 4. So it looks like the solution might be negative 1, 4. So we need to verify that that point actually works in both equations. So again, if we start with our first equation, remembering to put parentheses before we substitute, we get 2 times negative 1 plus 4, and we want to know if that equals 2. So we're going to get negative 2 plus 4, and that does give us 2, which does equal 2. So that is true. So that point does make our first equation true. What about our second equation? So we're going to take -2 times -1 plus 4, and we want to know if that equals 6. So we're going to get 2 plus 4 equals 6, 6 equals 6, which is true. So since this point -1, 4 is the only point that makes both equations true, the point -1, 4 is our solution to this system. Now, how do we know it's the only intersection point? Well, that's where our discussion early on with how we knew these were linear. So our graph is going to be a line, which means there's no way our graph can turn around and intersect in another point. Okay, so they've crossed here and they will never cross each other again.